All right, so this includes not only the answers, but also some solutions afterwards. So if you're curious, take a look. Right, page 323, the quiz. Number 4 is a little tricky. Here we have f of x, capital F of x, which is simply the accumulator function from 0 to x of this function, sine of t squared, and it's from 0 to 3. And so I want to think of this accumulator function. That means that capital F is the antiderivative of sine of t squared dt. And that's going to really help me consider this later on. So in part A, I want to estimate capital F of 2 using a trapezoidal method. Remember, capital F is simply accumulating the area under the curve sine of t squared. So from 0 to 2, I'm going to accumulate this area, and I want 4 subintervals. So I'm going to go from 0 to 0.5, 0.5 to 1, 1 to 1.5, and 1.5 to 2. Once I simplify this out, this will be my calculation for the trapezoidal method. Noticing that I factored out the 1/4 because each interval is length of 0.5, and I'm also dividing by 2 to calculate the area of my trapezoid, or the area of each trapezoid. I also want to find the derivative f prime of x, and here I can simply take the derivative of both sides, and when I do so, I can apply the fundamental theorem of calculus here rather easily. Now I want to know where capital F is increasing, and so that's obviously going to be where my derivative is positive. So I'll make a quick sign chart here. I want to know the critical points. Where is my derivative, capital F prime of x, equal to 0? And that will be when sine of x squared is equal to 0. So thinking about your unit circle, you know that sine is 0, at pi, and at 2 pi. So that means that x squared will have to be 0, x squared would have to be pi, and x squared would have to be 2 pi. When you square root both sides, you're going to get x equals 0, x equals square root of pi, and x equals square root of 2 pi. All of these are between 0 and 3, so they all work. But if you were to keep going, obviously if you keep rotating around your unit circle, sine will keep equaling 0. But past this point, when you square root, you're going to get something bigger than 3. And so you want to go ahead and stop at that point. Okay, so at this point I can create my sign chart. Here are my endpoints. Here are my critical points, square root of pi and square root of 2 pi. And I have positive between 0 and square root of pi, and it's positive between square root of 2 pi and 3. So those are the 2 intervals. Last but not least, I am told that k is the average rate of change of my function f from 0 to 3. And I want to rewrite my integral from 0 to 3 of sine of t squared dt in terms of k. So what I start out with is what they tell me. So k is the average rate of change between 3 and 0. So capital F of 3, capital F of 0 over 3. Now capital F is simply the accumulator function. So capital F of 3 is accumulating from 0 to 3 sine of t squared dt, and capital F of 0 is the accumulator function from 0 to 0, all divided by 3. Well, when I evaluate an integral from one point to itself, I get 0. So this ends up simply being 1/3 times the integral from 0 to 3 of sine of t squared dt. So that's what k is equal to. And then I can multiply by 3 on both sides to have 3k equals the definite integral from 0 to 3 sine of t squared dt. And what this tells me is that if I multiply the average value of my function, sine of t squared dt, times 3, that will give me the area underneath it from 0 to 3. Page 225, number 42. Here you want to split up your definite integral so that you can differentiate using the fundamental theorem. So if you're going from x to 2x, that's the same as going from 0 to 2x, 0 to the upper limit, and subtracting whatever was from 0 to the lower limit. And that'll leave you with what's between x and 2x. And now you can take the derivative of this whole thing, which you can apply then independently to these pieces here. So taking the derivative here, you're going to substitute in 2x for t, so it'll be 1 over 2x squared plus 1, which is, this is going to be 4x squared, and then by the derivative of this u, so it'll be times 2, and then here you'll simply be implementing 1 over x squared plus 1 and subtracting the 2. All right, page 325, number 48. This one is a little tricky, but you can relate it to something that I'm sure makes a lot of sense and will make it a lot easier. You're given the instantaneous rate of change of a function y with respect to x, dy dx, which is equal to sine of x over x. And you're also told that y of 5 is equal to 3. And what you want to do is write the function y in terms of this integral from 5 to x of sine of t over t dt. Now, if you think of dy dx as the velocity, and then this here as being the antiderivative evaluated at 5, in other words, position at 5, you'll notice that the integral from 5 to x is simply the displacement, if you will, because you're integrating the velocity function, the displacement from 5 to x. And so to find the position function, you will take the displacement and add on that initial condition, in other words, that at 5 the position was 3. So the position at 5 plus the displacement from 5 to any point will give you your final position at whatever x is. And so you can use this same model to build your function y that's just a generic function y. And so you have the initial condition plus the displacement from 5 to x of sine of t over t dt. Right, page 327, number 58, part B here. We're looking to show that the instantaneous rate of change of our function r of t must at some point be equal to 0. And whenever you're thinking about showing that the instantaneous rate of change has to be equal to some value, you are looking to use the mean value theorem, because the mean value theorem says, look, if you can find the average rate of change between 2 points of a continuous function, then you know at some point along that function, the instantaneous rate of change is going to be equal to that average rate of change. So we find the average rate of change on the interval from 0 to 24, and you'll notice that since r at 0 and r of 24 are the same, that average rate of change between those 2 points is going to be 0. So you know right off the bat you're looking to show that there's an instantaneous rate of change in some position that is 0, and so you're looking for 2 points in our table that have the same value, so that you can show that the average rate of change between those 2 points is 0, and that's what we have on the endpoints. So once you find that that average rate of change is 0, you can say since r is continuous, and we know r is continuous because r is differentiable, and if something's differentiable, then it must be continuous. So since r is continuous, the mean value theorem, and this is important to your answers, why I'm including it now, the mean value theorem guarantees that there is some c such that r prime of c is equal to this average rate of change, which is equal to 0. And so I cannot stress enough how important it is to cite the theorem that you are using to justify your claim. That'll always be a point. Your justification and mentioning a theorem as important as this one should go without saying. In part C, I'm given a function q which models the rate at which water is flowing, and it asks me to find the average rate of water flow. Well, that means I'm finding the average value of this function q, since q gives me the rate of water flow. So using the theorem we have for finding the average value of a function, I can find the average value of q by taking 1 over b minus a times the definite integral from 0 to 24 of q of t dt. And since we're not able to use the calculator here, here's the antiderivative after I go ahead and factor out that 0.01, and I'm going to evaluate 24 as 0 and subtract and then multiply. And so the average value of q is going to be 10.58 gallons per hour, because it is still a rate, so it is the average rate at which water is flowing. All right, page 327, number 60. Here you're taking part B, you're taking the derivative of g, and g is simply the accumulator function from 1 to x of f of t dt. So applying the fundamental theorem of calculus here by taking the derivative of this definite integral, and I'm going to end up with simply f of x. So g prime is equal to f of x, and therefore g prime of 2 is f of 2, and f of 2, by looking at the graph, is simply 1. So that's the rate of change of g at 2. And I'm going to skip ahead to d here because having taken the first derivative, it's easy to take the second derivative. So the second derivative, g double prime of x, is simply f prime of x. And since I'm looking for the point of inflection, I'm making a sign chart for my second derivative here. And I can see pretty easily that the points where g double prime changes from increasing to decreasing are at 1 and at 2. Notice that at 1 and 2, there's those little cusp points there. It's not defined. However, the first derivative is changing from increasing to decreasing. The second derivative is positive to the left of 1 and negative to the right of 1. And so based on that, I can say that my point of inflection is occurring at 1 and not at 2, since it is increasing on both sides, or sorry, decreasing on both sides of 2. And for part C here, I want to find the absolute minimum of my function g on the closed interval from -2 to 4 here. So to find the absolute minimum, I'm going to look at where g prime of x is equal to 0. Remember, g prime is simply f of x, and so f of x will be equal to 0 at -2 and at 3. Since I'm on a closed interval, I need only consider -2, 3, and the endpoint on the right, which is 4. So evaluating g at -2, which you did in part A, is simply that definite integral from 1 to -2, and that's -4.5. Evaluating at 3, you can see pretty clearly the area under the curve from 1 to 3 is going to be greater than 0, so it's greater than 0. And you already evaluated in part A g of 4, which is 2. So the minimum is clearly going to be -4.5, which occurs at x equals -2. Alright, so here we have number 54 on page 441. I'm dealing with a function that gives me the temperature, and I want to know in part B when the temperature is greater than 78. So I'm basically going to set my function equal to 78, and I want to find a solve for t when these are. Really what I want to do is find out when f of t minus 78 is greater than 0, or set it equal to 0 and identify if it's positive between those values. So really what you can do is you can just graph this function, so f of t, whatever that is, minus 78, you can graph it, and you can see where it intersects the x-axis, and then where it's above the x-axis is where it will be, where your temperature will be greater than 78. And so you'll see there's 2 points where it intersects the x-axis, and then in between those 2 points it's greater than 0, and so that's when the temperature is greater than 78. And so those are the 2 values I've labeled A and B that are in the solutions. Now, part C is sort of the tricky one here. I want to identify the cost to cool my house, and I know that it's going to cost me 5 cents per hour for each degree that the outside temperature exceeds 78 degrees Fahrenheit. Okay, so think about this 0.05 as being the dollars per hour per degree, right? Because it's how much it costs me per hour for every degree above 78. So what I need to do is I want to end up with dollars. I need to arrive at an expression which basically tells me the number of degrees that I am above 78 in terms of the length of time that that occurred for. And if you just line up your units here, you can sort of see what units you need to end up with just simply dollars. You're going to need degree hours. And you can find this by taking the definite integral from A to B of f of t minus 78, because this is going to give you the degrees above 78, and dt is going to be the interval, which is in hours. So these are going to be degrees above 78, and you'll end up with degrees times hours, or degree hours. In other words, this is sort of the accumulation of the number of degrees above 78 and sort of the length of time that that occurred for. So when you multiply these 2 values together, the degrees and the hours will cancel, and you'll simply have the cost for which you must be charged in order to cool your home. And that ends up being about $5.10. Again, a very tricky application of the definite integral, and one where you need to really make sure you understand the units that you're working with for both parts so that you can understand what your result will be, which in this case is going to be dollars. All right, here we are with number 55 on page 441. This one is rather tricky once you actually try to do the integral, so I'll go over this one a little bit. I want to find out the total number of people that have entered the park by 5 p.m. or when t is equal to 17. And so that will be the definite integral from 9 to 17 of the rate at which people are entering, e of t dt. So I can factor out the 15,600, and then I have 1 over t squared minus 24t plus 160. So I need to find the antiderivative of this function here, and this is rather tricky. But whenever you see a 1 over something and you notice that there might be a way to get something squared out of the denominator, it's worth trying for the inverse tangent, because the derivative of inverse tangent is 1 over 1 plus u squared du dx. So if I can somehow get this function to look like 1 over 1 plus something squared, then I can use inverse tangent. So playing around with the denominator here, let's consider this. I have t squared minus 24t plus 160. And I would love if this were a quadratic which was a perfect square. In other words, it was t plus or minus something squared. And in order for that to happen, I would need, let's just go and write this out. I would need both of the second terms of each of my factors to be the same. And I know that I'm going to add them together to be negative 24. So that would be negative 12 and negative 12. Okay? The problem with that is that when I multiply negative 12 times negative 12, I don't get 160, I get 144. However, that's okay because I can rewrite this instead of plus 160 as plus 144 plus 16. So when I consider the t squared minus 24t plus 144, I can rewrite that as t minus 12 times t minus 12. Or in other words, t minus 12 squared plus that 16 that I had left over. So I'm going to rewrite it here as 16 plus t minus 12 squared so that I have it more in the form of my inverse tangent derivative, 1 over 1 plus u squared. And now I simply need to factor out 16. So I'm going to go ahead and factor out 16. So let me rewrite this here. I'll have 1 over 16 times 1 plus, and to factor out a 16, I'll have a t minus 12 squared over 16. Like that. Now, since 16 is just 4 squared, I can rewrite this term here conveniently as t minus 12 over 4 all squared, as I have done right here. So now I have 1 over 1 plus something squared, and that is exactly what the derivative of inverse tangent u is going to be. Now the last thing I have to do is notice that I'm using the chain rule with u, so I'm going to take the derivative of u with respect to x. So when I consider, I'll write this out again, when I consider inverse tangent of u, and in this case u would be t minus 12 over 4, and if I were to take the derivative of this, I'm going to get 1 over 1 plus t minus 12 over 4 squared, which is exactly what I have here. However, when I take the derivative of the inside, I'm going to have t over 4 minus 12 over 4. The derivative of 12 over 4 is 0, and the derivative of t over 4 is 1/4. So if I were to take the derivative of this here, I'd get a 1/4 in front of my 1 over 1 plus u squared. That would be my du dx. So because I don't have a 1/4 here, I need to multiply out front by 4. So that when I take the derivative of the inside here, so if I took the derivative of this whole thing, the 4 times the derivative of the inside would end up being 1, and I would have exactly 1 over 1 plus u squared. So this gives me the inverse tangent of t minus 12 over 4 times 4, and I'm going to evaluate that at 17 and at 9 and subtract. Then I'm going to multiply by the 15,600. Use your calculator here to evaluate at 17 and at 9, and that will give me approximately 6,004 people that have entered the park up until 5 p.m. All right, for part C, I'm given this function h of t as defined here, and I want to find h prime of 17. I'm told h of 17 is somewhere around 3,725. So h prime, I'm going to take the derivative with respect to t. Now notice that I can split up my definite integral because I have a difference, forgetting the x here, because I have a difference of two things. And so when I take the derivative, I can apply the derivative to both of my definite integrals. And using the fundamental theorem of calculus, I simply have e of t minus L of t. So h prime is simply the rate at which people are entering minus the rate at which people are leaving. And so this can be interpreted simply as the rate at which the number of people in the park is changing. It could be that it's increasing if e of t is bigger than L of t, and it could be that it's decreasing if L of t is bigger than e of t. So I'll either have a positive or a negative change. So h prime of 17 is going to be e of 17 minus L of 17, and that's going to actually be negative 380. So that's the rate at which the number of people in the park is changing. So at 5 p.m., I have 380 people leaving, or people per hour, leaving the park. Now I want to interpret what h of t means. So h of t, if you consider my situation here, is the number of people that have entered the park between 9 and t, this is what we found in part A, minus the number of people that have left the park between 9 and whatever t is. So between 9 and 17, this would be the number of people that have entered the park between 9 and 5 p.m., and this would be the number of people that have left the park between 9 and 5 p.m. So when you subtract the two, you're simply going to end up with the total number of people that are in the park at that time. Hopefully it's a positive number. And it sure is, it's 3,725. So that's the number of people that are in the park at 5 p.m. I want to find the maximum number of people that are in the park for part D. And since I know that h represents the number of people in the park at any time t, I want to find the maximum of h. So I can find the extrema of h by looking at the critical points, so finding where h prime is equal to 0. H prime is simply e of t minus L of t. So when that is equal to 0, that will mean e of t is equal to L of t. So you use your calculator. You can either graph both of the functions, see where they intersect, or you can graph e of t minus L of t and see where that's equal to 0. That's going to be when t is 15.795. And I don't really want to evaluate h of t at 15.795 to see if that's bigger than the endpoints, in other words, using the closed interval test. So I can just do a quick sign chart here for h prime. So I notice that here are my endpoints, here's my critical point, and between 9 and 15.795, h prime is positive, and past that it's going to be negative, and so this is going to be my maximum. These are both going to be minimums, and so this leaves me with the absolute maximum since it is the only maximum on that interval. This was a tricky problem, but certainly worthwhile because if you can handle this, you can handle just about anything.